Hello, we are going to go over the next lecture, the third lecture in the magnetic semiconductors. So this is about the band structure of transition metals. So last time we went over the transition metals, so transition metal ions, and we can form from them good magnetic, good materials that have excellent magnetic properties. And this one is goes over the band structure of these transition metals and explains how we get these magnetic materials. So the band structure of the BCC crystal. So BCC stands here for the body-centered cubic crystal structure, and we can consider here the tight binding approximation. So in the tight binding approximation, we can account for the wave function of the atom. That can be written in this expression here. So this expression here is, in this expression we have here phi e alpha function, which is wave functions that we considered before. And these wave functions consider the wave functions of the electrons. And here we have this capital RE. This capital RE corresponds to the location of the nuclei of atoms here. Now, if we consider this tight binding approximation, in this approximation, the hopping integral between two sides, I and G, can be written with this line here. And in this line, we have here inside of the sum this integral, and this integral is just overlap between the alpha and beta atoms, and with H here standing for the Hamiltonian. And this Hamiltonian includes itself electron interaction, electron nuclear interaction, and so on. Now, if we consider this integral as a T alpha beta EG, this integral is called overlap integral, and it can be written in small form, in compact form like this here. Now, if we look, if we just write down this expression for tight binding approximation for BCC structure, and for this case for nearest neighbors only. For example, here this BCC structure is shown here, and in the BCC structure we have in the center atom that's located in the center, and we can consider here this as nearest atoms on the vertex of this cubic structure here. So in this case, the energy dispersion is written using this expression here. So we have here four neighboring atoms here for the central atom, and consequently we have here four terms in this expression. And the T here is the overlap integral. Now, if we draw this energy dispersion on the using the these points, symmetry points in the brilliant zone here, so we can draw here the band structure, and band structure looks like in this picture here. And consequently, we can write down here this density of states, and for density of states, we have here this picture, and it shows that density of states has maximum for the half filled in d electrons. Now, if we consider here this band structure for real metals, we have to consider now overlap integrals for different kinds of orbitals here. For example, here we have overlap for s electrons, and this overlap called just has one variant as is sigma. For p electrons, we have two kinds of overlaps, pp sigma and ppp. For d electrons, we now have, usually d electrons have orbits like this, and for this case we have three kinds of overlaps that's shown in this picture here. Now, if we consider all these kinds of this s, p, and d electrons overlaps, we can find this energy dispersion here, band structure, and this band structure is very complicated. So considering density of states, so density of states looks like this. Now it also doesn't have a peak for the half-filled ND electrons. And if we consider here density of states that are written here for S, P, and D electrons separately, we can find out from this that D electrons contribution is very large compared to S and P electrons. For example, here the total number of states per atom is 24.83, whereas for these numbers for S and P it's 0.43 into 0.46. Compared to these D electrons that have for one configuration 18 and for second configuration 3.95. So definitely for D electrons we have here larger value contribution to total number of states. So with this in mind, we can now just concentrate on D electrons here. And for D electrons we can consider, just as I said, these three overlaps, and if we consider these three orbitals overlap, we now can look up here this hopping integral for this 3D, 4D, and 5D elements. So for 3D elements, they start from titanium to all the way to copper, and for 4D electrons we have from zirconium to silver, and from 5D from hafnium to gold. So in this case, these black squares correspond to 3D elements, and these open squares correspond to 4D, and here circles correspond to 5D. And in this case, we can see that, for example, they have different energy dispersions here. Hopping integral values here. So for DDP, these lines are here. For DD zeta here, and for DD sigma, these hopping integrals are over here. Now, if we consider here the energy bandwidth for this case, now we can say that for 5D elements, we have larger values of bandwidth. And compared to 3D, for 3D case, we have smaller value of bandwidth, and these smaller values of bandwidth contribute to the ferromagnetism and antiferromagnetism of these materials. Now, if we calculate Fermi energy for these elements, 3D, 4D, and 5D, this graph looks like this. So Fermi energy is